This is the first mini lecture for section 7.1 of the textbook. We've spent the last few sections talking about fractions and rational numbers. So now we're going to extend what we mean by a number yet again by talking about decimals and real numbers. So today we're going to begin by talking about the decimal number system again. Before we get into that, we need to talk about negative exponents. So recall that if a is a number and m is a whole number, then we define a to the mth power as just the product of a times itself m times. And then if m is 0, a to the 0 is equal to 1. So now we extend that definition by defining a to the minus m as 1 over a to the m. So for example, 2 to the negative fifth is 1 over 2 to the fifth, which is 1 over 32. Or 10 to the negative third is 1 over 10 to the third, which is 1 over 1,000. Okay, in our culture, we represent numbers using the Indo-Arabic numeration system, which is a decimal positional system. The word decimal means that it's based on powers of 10. You'll think of the Spanish word diez. So for example, 7,485, that string of digits 7485, represents 7 times 10 cubed plus 4 times 10 squared plus 8 times 10 plus 5. Okay, we can put it a little bit differently by substituting the numeral 10. And then, we could also write this as just by writing out 1,110 and 1. So there's different ways of writing that. So the idea is to extend that system using negative exponents to be able to write non-integer numbers. So for example, 382.749 is 3 times 10 squared plus 8 times 10 plus 2 times 1 plus 7 times 10 to the negative 1, or 1/10, plus 4 times 10 to the negative 2, or 1/100th, plus 9 times 10 to the negative 3, which is 1,000th. So notice the pattern here. We're just counting down in the exponents. 2, 1, 0, negative 1, negative 2, negative 3. Okay, we could also use 0.1 or 1 over 10th, 1 over 10 or 1/10. 0.01 is 100th, 0.001 1,000th, and so on. Okay, so we're just extending our base 10 numeration system to handle non-integer numbers. That word decimal does not really refer to the 0.749 part, although often it's used that way. That word decimal means base 10. Okay, and in case you're wondering, we could do all of this in base 4 or base 5 or base 6 or any other base. We won't do that, but just as for whole numbers, it works exactly the same. Okay, so let's talk about what happens when we multiply by powers of 10. You probably know that it has the effect of moving the decimal point to the left or the right, maybe adding some zeros on there. So for example, consider 435.97. What happens when we multiply it by 10 squared? So this is something that I think you should read through just to make sure you understand. But what's happening here is we're writing the number in expanded form and then applying the distributive property to multiply that 10 squared to each of these powers of 10. And that has the effect of bumping each of those powers up by 2. So you add 2 to each of those powers. And when you put it all back together again, you've moved the decimal point 2 places to the right. Similarly, if we divide by 10 squared, you're multiplying everything by 10 to the negative 2. The negative sign should be up there, really. Which means that you're going to be knocking each of these exponents down 2, which has the effect of moving the decimal point 2 places to the left. So because we use a base 10 system, multiplying or dividing by powers of 10 has the effect of moving the decimal points. So when we multiply a number by 10 to the r, the decimal point moves r places to the right. When we divide a number by 10 to the r, the decimal point moves r places to the left. So for example, here I'm multiplying by 10 to the 5th and dividing by 10 to the 5th. And if you run out of places with digits in them, then you just have to add on some zeros, which is what we had to do in each of these cases here. Okay, so what we have now is two different ways of representing numbers that aren't integers. Fractions and decimals. So we have a lot of questions about that. So we've got these two systems in play. They provide us two different ways to write various numbers. So we want to know how they interact with each other. So for example, can every rational number be written as a decimal? Or in other words, can every fraction be written as a decimal? And if not, which can and which can't? How can you tell the difference? On the other hand, does every decimal expansion represent a rational number? So if I take something at random, 0.751, is that a rational number or a fraction? Can I write that as a fraction? What about repeating decimal expansions, like 0.3232322, where the 3 2's keep going on forever? Do those represent rational numbers or fractions? And if not, then which do and which don't? How can we tell the difference? How can I look at a decimal expansion and decide whether that's going to be a fraction or not, or a rational number or not? If we have a decimal that does represent a rational number, and we know it does, then how do we write it as a fraction? So if we know that this given decimal is a rational number, how do I figure out the fraction that corresponds to it? And then vice versa, if I have a fraction, how do I figure out the decimal representation? So we have a lot of questions here. How do these systems match up? Do they describe the same numbers all the time? And when they do match up, when we do have two different ways of writing a number, how do we go back and forth between the representations? Okay, so notice that we're even considering infinite decimal expansions, like 0.44444, where that 4 just keeps going on forever. So you're probably used to thinking about things like that because they come up on your calculator, but maybe you haven't really thought about what's involved there. When I write something like that, where the 4's keep going on forever, I'm talking about an infinite sum. 4 tenths plus 4 hundredths plus 4 thousandths plus 4 ten-thousandths, and so on forever. So the question is, does that even really make sense? Does it make sense to imagine adding up infinitely many numbers? And the answer is yes, it does, depending on the case. But it takes calculus to understand how that works, which we're not equipped to do in this class. So we're not going to talk about that, but I at least want to put it in your mind that that's something to think about. And, if you haven't taken calculus, and I'm talking really about perhaps calculus 2, or more likely real variables, which here at Saul Ross is a senior level course. If you have not taken a course like that, then you don't really know the answer to that question yourself. And if you're a middle school teacher teaching about decimals, you're potentially teaching about something that you don't quite have a complete understanding of yourself. And I think it's at least worthwhile knowing that there's a limitation there. Now, a decimal expansion that involves only finitely many terms, it cuts off after a certain point, is called a terminating decimal expansion. Okay, so if it cuts off after a certain point, we say it's terminating. And it's easy to see that any rational number any number represented by a terminating decimal expansion is a rational number. So I could just use the division by powers of 10 rule. So for example, 3.468, well, that's 3,468 over 1,000. And that's a fraction. Right? So any terminating decimal I can write as a fraction. So there's a partial answer to our question. But now I'd like to know which fractions have terminating decimals. Some do and some don't. Which ones do? How can I tell from looking at a fraction whether that decimal is going to terminate or continue on forever?